Okay, so let's have a look at quiz 4 and see what we have here. So it says at minus 15.7 degrees Celsius, the concentration equilibrium constant for a certain reaction is 9.8 by 10 to the minus 5. So that's a small equilibrium constant. Here are some facts about the reaction. Some of the reactants are liquids and solids. Okay, so they're not going to appear in that expression for Kc. The constant pressure molar heat capacity Cp equals, that's really got nothing to do with anything. And it says if the reaction is run at constant pressure, 69 kilojoules of heat are released. So it is a exothermic reaction and delta H is less than 0. It says using these facts, can you calculate Kc at minus 37? So how do we relate these things? Well, we have to do log K1 on K2 is equal to negative delta H on R, 1 on T1 minus 1 on T2. So what do we have? We have K1, check. We are trying to find K2. We have the enthalpy of this reaction. So we have delta H, check. R is the ideal gas constant, so we have that guy. And then finally we need T1 and T2. So there is T1, so we got that guy. And we have T2. T2 was minus 37 degrees Celsius. Now, when it comes time to actually do this, we'll have to convert those into Kelvin. So we have everything that we need except for this one thing, so I can solve that. All right, so yes, I would be able to solve this for the temperature is minus 37. So I'm going to put a yes in there. Okay, if you said yes, then enter your answer at right. Round it to 2 significant figures. So a few things that I have to keep in mind here is those temperatures need to be in Kelvin, which we already talked about. And then the heat of the reaction has to be expressed in joules per mole. And we also need to make sure we use the correct value for R. So let's go ahead and kind of get the two temperatures into Kelvin. So I can pop my calculator up. This is going to take a little bit. So we've got minus 15.7 plus 273.15. So T1 equals 257.45 Kelvin. And then T2 is that minus 37. So we got minus 37 plus 273.15. So T2, 236.15 Kelvin. Okay, so it's colder. And this is a exothermic reaction that generates heat. So heat is a product. So if we make it colder, it's going to make more. It's going to move to the products because it's going to try and raise the temperature. All right. So K1 we've got. K1 is 9.8 by 10 to the minus 5. K2, which we're going to expect to be bigger than K1 because this reaction is going to try and raise the temperature and make heat. That's what we're going to solve for. Delta H, remember I said it has to be in joules per mole, so that's going to be 69 times 10 to the 3 joules per mole. And remember, delta H is negative, right? Because it's an exothermic reaction. That heat is released. That is joules per mole. And then finally, R is 8.314 joules per mole per degree Kelvin. So let's set all of that up and then we will solve. So we're just kind of taking our time here. Don't want to make a mistake. Alex really hates it when you make a mistake. So log of a K1, 9.8 by 10 to the minus 5 over K2 is equal to negative of a delta H, which is negative of minus 69, because that's not really in scientific notation, is it? I just was converting from kilojoules, times 10 to the 3 joules per mole, divided by 8.314 joules per mole per degree Kelvin. Okay, so that's my delta H on R, multiplied by 1 on T1, which is my 257.45, minus 1 on 236.15, and that's going to have units of 1 on Kelvin. Okay, so this is interesting. The joules per mole clearly cancels, joules per moles, and then we've got 1 over Kelvin, which is just straight up Kelvin. So then Kelvin times by 1 on Kelvin, that's going to cancel. So that ends up being unitless, which is good because all log quantities should be unitless. So our expression, pretty straightforward, log of 9.8 by 10 to the minus 5 on x, our K2, is equal to 69 by 10 to the 3 over 8.314 multiplied by 1 on 257.45 minus 1 on 236.15. And then a variety of ways you can solve this, and probably the easiest way I would say would be to maybe use like an online solver, or you can use the solver in your calculator. So I'm going to do that now. My calculator requires that the expression equals 0. So pretty straightforward for me to do that. A log of 9.8 by 10 to the minus 5 on x minus 6. I keep doing the 6.9, don't I? 69 times 10 to the 3 on 8.314 by 1 on 257.45 minus 1 on 236.15, and that whole thing equals 0. Now, I'm just doing that because my calculator requires that when I use the expression that it always equals 0. You know, kind of like we always, when we solve for the quadratic, we always do ax squared plus bx plus c equals 0. It's just the kind of quirk of my particular calculator. So I'm going to go math, solver, and then carefully start putting this in, right? So there's the equation. So it is log of 9.8 by 10 to the minus 5 on x, which is what we're solving for, minus 69 by 10 to the 3 on 8.314 times parentheses 1 on 257.45 minus 1 on 236.15, and then close the parentheses. So that's a lot to enter, so you want to take your time. Enter that, and then now we have to give it a guess. Well, we know that it's probably going to be bigger, well, it is going to be bigger than 9.8 by 10 to the minus 5. So I'm going to use that as my starting point, and then I can set the bounds if I want. I don't have to, but I know that k's are never going to be 0, right? They're never going to be negative, sorry. So I can set the lower bound as being 0, and then I'll set the upper bound as being a really big number. For me, I have to put my cursor on the row where it specifies the x, and then I go alpha, solve. And there we go, there's my answer there. So I'll quit out of this. So it decided that x equals 1.79 by 10 to the minus 3. So remember it said that it was two significant figures, so this will be 1.8 by 10 to the minus 3, which is bigger than 9.8 by 10 to the minus 5. So I feel pretty confident that I got it right. Remember again, k's don't have units, so we don't have to worry about that. So that's it, right? 1.8 by 10 to the minus 3. It's a lot bigger. It's like 100 times bigger. All right, so we got that one. If you said no, can you at least decide that KC will be bigger, smaller, or whatever? Yes, and KC will be bigger, right? So we already know that. So we got it all, right? 1.3 by 10, 1.8 by 10 to the minus 3. And that's it. Everything is done. Okay, it all makes sense. So a few things to pay attention there. Got to get the sign on delta H correct. And I knew right from the beginning, because I thought about this system being at a lower temperature, that K2 was going to be bigger than K1. So I knew I didn't make a sign error along the way. All right, other than that, all is good. Convert your delta H to joules. Make sure your temperatures are in kelvins. Don't mess up entering it into the calculator. Use either Wolfram Alpha or the solver feature for your particular calculator. Saves you doing a bunch of algebra. All right, let's have a look at this one. It looks like we've got a written description of the reaction. Steam reforming of methane or methane, CH4, produces synthesis gas, a mixture of carbon monoxide gas and hydrogen gas. So CO and H2 are going to be our products, and our reactants are going to be methane and steam, right? So an industrial chemist studying this reaction fills a 2-liter flask with 2.7 atm of methane and 3.5 atm of water vapor. Okay, so initially we have 2.7 of that, we have 3.5 of that, and we have none of those things. And then it undergoes a change, and at the end, it says when the mixture has come to equilibrium, measures the partial pressure of carbon monoxide to be 1.4. So we've got to balance this guy, right? And so what you can kind of see here is that at the moment, it doesn't really balance for the hydrogens, because we've got 6 hydrogens on the left and we've only got 2 on the right. So I'm going to need 3 of those guys. And then now it balances for carbons. Yep, 1 on each side. Hydrogen, 6 on each side, and the 1 oxygen. So the carbon monoxide went up by 1.4. So that means that the hydrogen must have gone up by 3 times 1.4. So 3 times 1.4. So the hydrogen must have gone up by 4.2. Now, what about the reactants? Well, it's all 1 to 1 to 1 as far as methane, water vapor, and carbon monoxide is concerned. So carbon monoxide went up by 1.4. Methane and water must both have gone down by 1.4. So now I've just got to do the math on that. 2.7 minus 1.4 is going to give me 1.3, but I don't trust myself. So we're just going to double check just in case. And then 3.5 minus 1.4 is going to give me 2.1, but we're going to double check. There we go, 2.1. And so now we have the equilibrium partial pressures of every component, and we can go ahead and calculate a Kp. So all we've got to remember is that the Kp expression is going to be the pressure of hydrogen, all cubed, multiplied by the pressure of carbon monoxide, divided by, and we've got to keep this whole bottom row in parentheses, the pressure of methane, multiplied by the pressure of the steam. And that's it, right? And so when I look at this, I see that, I've got a decent amount of both reactants and products. So Kp is going to be like not too big, not too small. So it's not going to be 10 to the minus 6, but it's also not going to be like 10 to the 10, right? It's going to be kind of intermediate. It's going to be like a number bigger than 1, but it's going to be modest, would be my guess, right? So we've got 4.2 cubed multiplied by 1.4 divided by 1.3 multiplied by 2.1. And you want to make sure you got your parentheses on the bottom line there, and that you actually use the equilibrium values. All right, let's see what we get for Kp. Remember, Ks have no units. So just carefully putting this in, 4.2 cubed times, oh, we don't like that, do we? Need to hit this extra button, times 1.4 divide, put this whole thing in parentheses, 1.3 times 2.1, and remember a number that's kind of like not too big, not too small, right? 38, okay? So 38.0, we're asked for two significant figures, so 38 is perfect, right? Not a huge number, not a tiny number, just a kind of, you know, Goldilocks number right in the middle there. Okay, let's have a look at this one. Suppose a 250 milliliter flask is filled with 1.6 moles of N2 and 1.1 moles of NO. Oh, interesting. So a little bit of reactants, a little bit of products, and then it's going to kind of, something is going to happen. Now, what I notice here that is interesting is that there's no O2, right? So what that means is that I know that it's going to shift to the left because initially there is no O2, right? So we got 1.6. Now I'm going to work in molarity here, right? So we only ever work in molarity or ATM. And in this case, they gave us moles and a volume, so we know we're going to be working in molarity. 1.6 moles on 0.250 liters. So you're basically going to times that by 4, aren't you, right? But we're going to do it, again, we do the math in our calculator just in case. Try not to do too much mental arithmetic. So that was 6.4 moles per liter N2 to begin with. And then what do we got? 1.1 NO. 1 mole of NO in a 0.25 liter container. And again, we know this is going to be 4.4, but we'll still double check. There we go. No surprises there. Just being really cautious. So 6.4 of that guy, 4.4 of that one. Now we know what's going to happen, right? It has to go to the left because I've got no O2. It's impossible for it to move to the right. So the change is going to be a shift to the left. So N2 is going to go up by X, O2 is going to go up by X, and NO is going to go down by 2X. So when this comes to equilibrium, I'm going to have 6.4 plus X of that, and 4.4 minus 2X of this. Now let's see if there's any information in here about what X might be. Complete the table below so that it lists the initial molarity of each compound. We did that and we got it right. The change in molarity of each compound due to the reaction, and the equilibrium molarity of each compound after the reaction has come to equilibrium. Use X to stand for the unknown change in the molarity of O2. You can leave out the symbol for molarity. So this is really important, like what they say that X is going to stand for, because I'll show you something. If we had it that X equals the change in the concentration of NO, then our table would look a lot different, right? What would happen is that these would still need to be in the ratio of 1 to 1 to 2, these changes. So it would end up having to look different, right? This would go up by half an X. This would go up by half an X. And then this would go down by X. So you have to be clear about what they are letting X stand for. Now, I don't do fractional X's, but Alex will do that. And so they just want you to understand how the mole ratios work. Now, in our case, how we set this up, was much more sensible. We said there's one of those, so that's 1x that goes up by, and there's one of those, so that's 1x that goes up by, and there's two of those, so that's 2 of x that goes down by. And that works in this case because the change in O2 is x. You'll also see here that they haven't specified whether it was an increase or a decrease, so you don't have to put the minus signs in and the plus sign in. All right, so just read the question carefully. It's all about mole ratios and understanding that if you have 0 concentration on one side, that's the way that it's going to move. Okay, so so there's your answer there. We just have to fill in the table. Like I said, the only thing that's different here is you don't need those pluses and minuses for Alex to be happy. You can put them in and I'll still grade it as being correct. Okay, nitrogen monoxide and water react to form ammonia and oxygen like this, and it's nice, it's balanced, so we don't have to go ahead and balance it, right? The reaction is endothermic. So what you should realize is that means that heat is a reactant. And so we can use Le Chatelier's principle to think about how changing the temperature will shift the equilibrium. And when we change the temperature, we actually we change the value of the equilibrium constant. The fact that it is endothermic also means that delta H is greater than 0. So it says, suppose a mixture of NO, H2O, NH3, and O2, so that's everything, it's all of the components, has come to equilibrium, so Q equals K. Predict what change, if any, the perturbations in the table below will cause in the composition in the mixture in the vessel, and also decide whether the equilibrium shifts to the right or to the left. So we're at equilibrium and we do something to it. All right. So it says the temperature is raised. So we add heat. What does adding heat do? It's going to cause the equilibrium to shift to the right because we want to consume that added heat. So everything on the left will go down and everything on the right will increase. So the pressure of NH3 will increase. And the equilibrium will shift to the right. Now it says the temperature is lowered. So what we're going to do is we're going to take away some of that heat. And so the system will move to the left to replace the heat that we're taking away. So if it moves to the left, everything on the left will increase in pressure. Everything on the right will decrease. Okay, so what's going to happen? The pressure of NO is going to go up. It will increase. Right, and the equilibrium will shift to the left. So it's not too bad, just a little bit of Le Chatelier's principle there. Right, also understanding what we mean by the term endothermic. Okay, this one is one where we don't have a balanced equation, so we're going to have to figure that out. It says sulfur dioxide, so SO2, and oxygen react, so just remember that it's O2, to form sulfur trioxide. Always want to be careful about not confusing your sulfur dioxide and your sulfur trioxide. Okay, so we got to get this guy to balance, and they don't at the moment because we have 4 oxygens on the left and only 3 on the right. So if I put 2 of those there and 2 of those there, then it all works out, right? So 2 sulfurs, 2 times 2, that's 4, plus another 2, that's 6 oxygens. 2 times 3, that's 6 oxygens. So that's good. All right, an industrial chemist studying this reaction fills a 125-liter tank with 19 moles of sulfur dioxide and 15 moles of O2. So we know initially there's none of that stuff. All right, so initially we've got none of that. Now they gave us, what kind of data did they give us? They gave us volume and moles. So we're going to be working in molarity. So I'm going to write my initial change equilibrium on the right here because I kind of put that in a stupid position. So let's go ahead and figure out our initial molarity of sulfur dioxide. So we've got 19 moles in 125 liters. So that's going to give me 0.152 moles per liter. All right. So 19 mole of SO2 in 125 liters gives me 0.152 moles per liter. We're just going to give that an uppercase M. Remember, you only ever work in molarity or atmospheres when you're doing KC and KP calculations respectively. If they give you moles and volumes, you know you're going to be working in molarity, right? Most of the time. Okay, now we've got 15 moles of O2 into the same 125 litre container. 15, 125, and that gives me 0.12, and it's just 2 sig figs anyway, so 0.12. And we had none of the SO3 to begin with. So we know what way it's going to go, right? It's going to go to the right. So what's going to happen? That's going to go up by 2x. That will go down by x. And this will go down by 2x. Okay, fine. So at the end, we've got 2x of that, 0.12 minus x of this, and then 0.152 minus 2x of that. So there are our equilibrium amounts. So the question is how the heck do we figure out what x is? There must be some more information in the problem. So let's go back up to the problem. It says when the mixture has come to equilibrium, the amount of sulfur trioxide gas is determined to be 5.7 moles. So at equilibrium, we have 5.7 moles of SO3 dissolved in 125 liters. So the equilibrium molarity of the SO3, 5.7 divide 125, 0.0456. Okay, and that's equal to 2x, right? So 2x equals 0.0456 molarity. So x is half of that, right? So on 2, there we go, 0.0228. So now we have everything we need to solve for KC, all right? So let's just go ahead and do that. So KC is going to be equal to the concentration of SO3, and that has to be squared, divided by the concentration of SO2, and that has to be squared multiplied by the concentration of O2. So it's just products over reactants, right? And everything has to be raised to the power of its stoichiometric coefficient. So the concentration of SO3, we just got that. That is 2x. So that's that guy. So 0.0456 squared. And then the concentration of SO2, that was 0.152 minus 2x. And that has to be squared. And then the concentration of O2 is 0.12 minus 1x. And then there's x there, 0.0228. Now you want to make sure you put that whole bottom line in parentheses. So here we go, right? 0.0456 squared divide parentheses 0.152. We're going to take away 2x minus 0.0456, close those, square them, times new parentheses 0.12, that's the concentration of O2, minus X, 0.0228. Close those parentheses, close off the whole bottom line, and we're going to get our number. Now, at the end of this, what we know is that, yeah, we wouldn't expect it again to be too big or too small because we have a little bit of both, right? There we go, and it probably says to give this to 2 sig figs, but we'll have a look up there. So Kc is 1.9 to 2 sig figs. What does it say? 2 sig figs. Yeah. All right, and so that kind of makes sense. We have a decent amount of both reactants and products, and yeah, that's it really. That's all you got to do. You just got to kind of work through it. 2 problems in a row there that were somewhat similar. Okay. Oh, it looks like we've got the same type of problem again, but we have different sort of numbers in here. So sulfur dioxide, yeah, and oxygen, yeah, react to form SO3, so we know how to balance that one. Okay, we'll put our initial over here now. It says an industrial chemist studying this reaction fills a 5-liter flask with some sulfur dioxide and some oxygen. All right, so none of that. So we've got to work in here. So 2.6. Oh, we're just doing this is easier. See, it's Kp. I'm going to solve for Kp. So we don't need this volume here. We can just work with the ATMs. Wonderful. So initially we've got 2.6 of that. 2.9 of that. So we all know what way it's going to go. It has to go towards the SO3 because that's a 0. So that's going to go up by 2x, which means that this is going to go down by x, and then this is going to go down by 2x. And then when it comes to equilibrium, it says that the sulfur trioxide is 1.3. So 1.3. There we go. Which is equal to, of course, 2x. So this is not too bad. This is a lot easier, in fact. So this is going to be 2.6 minus 2x, and this is going to be 2.9 minus x. And we know that 1.3 equals 2x. So then x is going to be equal to, well, we know we should do the math, though. It's going to be equal to half of that. So, which is going to be 0.65, but x is equal to 0.65. So there we go, right? So the partial pressure of SO2 is going to be 2.6 minus 2x, which is 1.3. So that's just going to give me 1.3. The partial pressure of O2 is going to be 2.9 minus x. 2.9 minus x, 0.65. So that will be 2.25. We should check all of these things, shouldn't we? But I mean, you should check all of them. And then finally, we know that the partial pressure of SO3, because it was given in the problem, is just 1.3. Okay? And they were all ATMs, aren't they? Now, if you're sharp, you already know the answer to this one. All right, so what is our expression for Kp? It's going to be the partial pressure of SO3 squared over the partial pressure of SO2 squared multiplied by the partial pressure of O2, and that's going to look like that. That has to be in parentheses. Okay, so SO3, 1.3 squared, SO2, 1.3 squared, and then O2, 2.25. So this is where I said if you're sharp, you'll see that these will cancel. So that's just going to give me 1 on 2.225. So Kp, it's going to be like not a really big number, not a really small number, right? It's going to be a little less than a half. 1 on 2.25. There we go. 0.44 to 2 sig figs. Okay, so interestingly, what you see here is that Kp doesn't equal Kc, yeah? And we know that we have a little formula for relating the two if we really wanted to do that interconversion. All right, what is this one? So a certain chemical reaction, the standard Gibbs free energy of the reaction is minus 132 kilojoules. Calculate the equilibrium constant for this reaction, round your answer to 2 significant figures. So this is a very negative delta G, so I would expect a pretty big K. It's a spontaneous reaction. So how do we do this? We have a little formula. Delta G naught, which is for standard, is equal to minus RT log K. We have delta G. R is the ideal gas constant. We also have the temperature. We just got to make sure that everything is in standard units. So delta G needs to be in joules. So delta G is equal to minus 132 by 10 to the 3 joules. And that is equal to negative R, 8.314, times by T. So it's 10 degrees Celsius, 10 plus 273.15. 283.15 for my T. And then we've got log K. So a couple of ways of doing this. You can do algebra, or you can use a solver. I'm going to do algebra just to demonstrate that. So we got minus 132 by 10 to the 3 over minus 8.314 times 283.15 will give me log K. And we'll see what that equals. Minus 132 second function e to the 3 divide parentheses minus 8.314 times 283.15 close parentheses, and there we go, 56.07. And so now we have to just get K. We don't want log K. So K will be equal to E to the 56.07. And I'm just going to do that without rounding. So I'll just go second function E, second function answer, and it'll just pull up that whole answer without rounding. Hit enter, and then there we go, 2.2 by 10 to the 24. So K is a very big positive number corresponding to the very large negative number for delta G. So I'm very happy with this, that I got a big number. If I got a number a lot less than 1, I would be going back and checking my math and making sure that I hadn't made a sign error. All right, so that is quiz 4. Hope you found that helpful.